Okay, good morning. So I think that people are supposed to come, they're already here, so we can continue. So if you remember last time I talked about how to write a complex number in its polar form. And I told you that this is probably the first time we are making something more complicated, yes? And the examples that I gave was actually quite famous numbers, but let me choose two problems from the book and tell you about those, and then we can go to the next lesson, which is actually important. So let me choose two problems from the book, and I can also refresh your memory about that. So I give you this number, z equals to 2 minus I, and I ask you to write this in its polar form, yes? So if you remember the polar form of a complex number, it's of course given to you in the formula sheet, but this is what it is, yes? R cosine theta plus R sine theta. If I ask you what R is, you would say R is the absolute value of my complex number, and if I say what theta is, you would say it's the argument of the complex number. So that is what we call the polar form. Hopefully today we will cover why changing this simple number to a little bit more complicated form is valuable. Okay, so if I ask you to find the polar form for this, you need to calculate these two. Okay, so the first thing is very simple. So when you calculate R is absolute value of z, and you already know what to do. You need to write square root and take the real part, square it. Take the imaginary part, which is minus 1, square it. Be careful, imaginary part is not I, is the coefficient of I. And then becomes square root of 4 plus 1 and becomes square root of 5. So R that I am looking for is the square root of 5. But in the examples that I gave to you before, I chose them from famous numbers so that I can use my memory. Of course, you can probably help me to use your calculator here. But the second thing is to find the argument. For the argument, I told you it's good to always to sketch where this is located. So the real part is 2, the imaginary part is minus 1. So this is the real part, 2, the imaginary part minus 1. So this is the location of this point, and you draw the vector from the origin to this. And then this is the argument, and I always use this convention from 0 to 2 pi, or from 0 to 360 degrees, it's better. So I will start from this real part, and I have to go up to here. This is the argument that I am looking for, theta. But I told you that usually it's better to find the smaller angle here. So let me take this smaller angle, I call it alpha. And you always use tangent, so you don't need to think about it. It's always tangent, but you need to consider the lengths, not the signs, yes? So I would say the tangent alpha is the length of the opposite side. The length of the opposite side is of course 1. And then, tangent alpha is equal to divided by the length of the adjacent side, which is 2. But this is not one of those angles that I have it in my head. So what you have to do, you have to use your calculator. And in that case, if I want to keep it exact, so it becomes tangent inverse of 1 over 2. But tangent inverse 1 over 2 is this angle alpha, but you are looking for theta. So theta becomes, I don't know, for example, if you go to degree mode, you can write 360 degrees minus tangent inverse of 1/2. Yes? So in that case, if I ask you to keep it exact, that is the exact argument, but of course working with this one probably is a little bit hard. This is why you can put this number in the calculator, and I check it in the book. So they have found this angle to be 333 degrees, okay? So this is approximately 333 degrees. But of course I have to be careful if I ask you, for example, they have rounded up to an integer. We can keep 1 decimal points, 2 decimal points, depending on the problem. And then you put it in that formula, and that's it. And I told you that you shouldn't simplify it because it's clear. If you simplify it, you get this number back. So z becomes what? R. R is square root of 5. And then you write cosine 333 degrees, or if you want, you can write it in radians. It was easier because the book was working in degrees, so I wrote it in degrees. But of course, because this is approximate value, this is not exactly z, but it's very, very close to z. So that is the polar form of that complex number. Yes? Is that clear? So even if the angle is not a famous angle, you have to do it in that way. Okay, but now the next topic that we want to teach, I want to teach two subsections, both of them are important. So there is a very nice relation. If I have the complex numbers in the polar form, and if I ask you to multiply them, so if I ask you to do arithmetic on them, yes? So you can simply add these numbers, subtract them, multiply them, and divide them, yes? But for multiplication and division, there is a very nice relation that appears. Yes, so I want to discover that one. And the topic is multiplication and division of complex numbers in polar form. Yes, so multiplication and division in polar form. That would be the topic here. So let us just do it together once for all. So I give you two complex numbers, z1 and z2. I assume that they have already been written in the polar form. So what does it mean? It means that someone has done it for us, and for example, the absolute value is r sub 1, and the argument is theta 1. And then you have I sine theta 1. And then you have R2 cosine theta 2 plus I sine theta 2. What I want you to understand, that's not a new lesson, but it is important to see what happens if we multiply them. It turns out to be a nice formula at the end. So if I want to multiply them, what should I do? I take this number and multiply it by this number. R1 will be multiplied by R2. Yes? And then this expression will be multiplied by that expression. Yes? And then I start multiplying as usual. So I will keep R1 and R2. Be careful, R1 and R2 are real numbers because they are absolute values. But then I multiply this by that, it becomes cosine theta 1 cosine theta 2. If you don't mind, I should multiply this by that if I want to keep the order. But let me multiply this by that first. Because then I times I becomes I squared becomes negative 1. And sine theta will be multiplied by sine theta 1 will be multiplied by sine theta 2. Yes? So remember, I multiply this by that. I also multiplied this by that. There are two more terms that I have to consider. One of them is take this one and multiply it by the last one. The other one is to take this one and multiply it by the first one. So if I multiply this by the last one, it becomes plus I sine theta 2 cosine theta 1. And if I multiply this by that, it becomes I sine theta 1 and then cosine theta 2. And just simple multiplication. The reason that minus sign appears here because you will see I times I. Okay, but I hope that at least this combination looks familiar to your eyes, yes? We had this before in chapter 2. That is the cosine of the addition. This is the addition formula for cosine. And if you factor an I out here, that would be addition formula for sine. So I will take this one and write I. Let me write this one first. I sine theta 1 cosine theta 2 plus sine theta 2 cosine theta 1. Yes? And then this one is the addition formula. So if you remember for cosine, it was different. If I have addition formula, a negative sign appears. But for sine, it's the same. So this is an addition formula for cosine, and that's the addition formula for sine. So it becomes what? R1, R2, and then what happens? This becomes cosine theta 1 plus theta 2, and then plus I sine theta 1 plus theta 2. So that's a nice result, you know. So if you multiply two complex numbers, of course, you see I did it the normal way, but the result is interesting. So what you need to do, you just multiply the absolute values, but you add the arguments. So that is a nice relation. So I would say that from here now, if you want, you can write this. So remember, this is the way that you do. So if you can say Z1, Z2 is R1, R2, and then you have cosine theta 1 plus theta 2 plus I sine theta 1 and theta 2. Yes, so that is the formula, which is of course also included in the formula. So the lesson is that if I have two complex numbers in the polar form, this is a nice result to remember. If you multiply them, what happens to the absolute values? The absolute values are being multiplied, but what happens to the arguments? The arguments are added. Yes? So if you have two complex numbers in the polar form, it's extremely simple to multiply. It might be even simpler than the other scenario. So for example, I don't know, if I give you a complex number in this form, z1 is equal to square root of 2, and then I would write cosine pi over 3 plus I sine pi over 3. That is a complex number in its polar form, and let me give you another one. So I will take this one, 3 square root of 2, and then I would write cosine pi over 6 plus I sine pi over 6. These are two complex numbers in the polar form, and I ask you to multiply them. So if you multiply them, what will happen? Z1, Z2. I learned that I have to multiply the absolute values. So square root of 2 multiplied by square root of 2 becomes 2, and then another 3 becomes 6. Yes? But then I don't need to start doing this long process once more. I realize that I can write cosine. What I can do, I can just simply add the arguments. Yes? Of course, I can stop here. The multiplication is done, but you see immediately that becomes much simpler, yes? Because in this case, this becomes pi over 2, which is 90 degrees. That's also the same angle. But we know that the cosine of 90 is 0, sine of 90 is 1. So this becomes 0, this becomes 1 times I, which is I, and the answer becomes 6I. Yes, so whenever you have two complex numbers in their polar form, if you multiply them, remember, you just multiply the absolute values, but you add the arguments. Okay? For the division, more or less, we have the same thing, yes. But I think you probably will be able to predict what will happen if we divide. For example, I give you these two complex numbers and I ask you to divide them. Okay, instead of dividing them, I can divide them, of course, but I think it would be good if we see that what is the reciprocal of a complex number in its polar form. So, for example, if I give you z2 to be this number, if I ask you, what can you write about 1 over z2? Let us see what happens for 1 over z2. And then, of course, what is the goal? Because if I know what is 1 over z2, then z1 divided by z2, which is my main goal to calculate, I can write it as z1 multiplied by 1 over z2. If I already got what is 1 over z2, I can replace it here, and then I use the product formula again. Yes? That's the goal. So let us just calculate this one. Of course, this is very strange. I start with 1 over z2. So if you don't mind, let me just write z to see what happens if z is r cosine theta plus r sine I sine theta. Yes? So the question mark is, so let me write this, let me make it clear. So if z is r cosine theta plus I sine theta, what is 1 over z? So 1 over z is equal to 1 over r cosine theta plus I sine theta. Okay, so do you have any idea what to do? This one I don't have any problems because that's a real number. 1 over r can be written as 1 over r here. And then, what can I do? I can write cosine theta plus I sine theta. And then I have 1 here. Okay, how should I proceed? Because this number is neither the Cartesian form, it's not a standard form, it's not a polar form, yes? The polar form should be in the numerator. So what can I do? As usual, if you want to divide complex numbers, what was the rule? You multiply by the conjugate of the denominator, yes? So what I do, I will continue and write 1 over r, 1 over cosine theta plus I sine theta, and then I multiply it by its conjugate. Okay, I have to multiply and divide so that nothing is changed. And then I have 1 over r, and then multiply 1 by there so it is just the same thing. But when I multiply this by that, it becomes a conjugate pattern. Yeah? So it becomes the first one squared minus the second one squared. And then this becomes 1 over r. The numerator, I cannot do anything with that, so let me just keep it for the time being. But this one is cosine squared theta. This becomes I squared, which becomes negative 1. There is also a negative sign here, so it becomes positive. And then I have sine squared. Yes? And then, of course, everyone knows that sine squared plus cosine squared is just 1. So what happens if I simplify that? It becomes 1 over r cosine theta minus I sine theta. Yes? But this is not exactly the polar form, because in the polar form we have to have addition in the middle, so we have subtraction here. So how can I get rid of that minus sign here? That is also simple. So I can write it 1 over r. Instead of cosine theta, I hope that you agree that I can write cosine minus theta, because cosine minus theta and theta are the same. But this minus sign, I can put it next to sign and write this positive. Yes? Is that clear? So what happens if I start with a complex number with this polar form? Its reciprocal in polar form is this. What does it mean? It means that the absolute value of this number is 1 over the absolute value of the original number. But if the argument of the original number is theta, the argument of the reciprocal is minus theta. Yes, is that understandable? By the way, these provide you a lot of interesting ideas about geometry in the complex plane. For example, let me just see that how I can use this. For example, if I tell you that this point is z, by the way, that's I could have asked this question before. So if this is z, z is a point in the plane, 1 over z is also a point in the plane. But where is it? If I give you this is the location of z, and I ask you where is 1 over z? It was not that easy question in the beginning. Of course you can answer. For example, if I give you this and I ask you where is 1 over z? So you know where this one is. The real part is 1, the imaginary part is 1. So here is z. But if I ask you where 1 over z is, what you do, you calculate it. So it becomes 1 over 1 plus I. But you multiply it by the conjugate. Yes? And the answer becomes 1 minus I, and then this becomes 2. So then you will see that this becomes 1 over 2 minus 1 over 2I. Yes? And then you find it. 1 over 2 is here because that was 1, that was 1. 1 over 2 is here, minus 1 over 2 is here, and then you suddenly see this is where 1 over z is located. So this was your z, but now this one is 1 over z. Is that clear? And then you see in the picture, I hope that you agree what this angle is. This is 1 and this is also 1. Pi over 4. What this angle is. Because that was 1/2, that is also 1/2. So from the magnitude point of view, that's also 45. But this 145 is in this direction, but this 45 is in the negative direction. And that is what we just got there, yes. So take this, if I ask you what is the argument of z, you will tell me the argument of z is pi over 4. If I ask you what is the argument of 1 over z, you can talk about this angle, but equivalently you can talk about this angle. Yes? So this angle is minus pi over 40. Pi over 4. And that is what is predicted here. If I start with a complex number whose argument is theta, and if I calculate its reciprocal, the argument of the reciprocal is minus the argument of the previous one. And this is more or less what you see. As for example, if I tell you that this is z, if I ask you to draw 1 over c, what do? You would say that okay, if this is theta, I will find minus theta first. Minus theta is this angle. Somewhere here, yes? It's minus theta. And the only thing that I need to do, I need to know what is the length of 1 over z. The length of 1 over z is the length of 1, if you remember we had this before, divided by the length of z. But the length of 1 is just 1, the length of z. So what you need to do, you measure this one, whatever this is, you find the reciprocal, and then separate it here on this line. For example, if this is 5 units, the reciprocal of that is 1/5. So you go here and choose a point whose distance to the origin is the reciprocal of this distance. For example, I don't know, here. This becomes 1 over z. Is that understandable? So that will give you a lot of good understanding about the geometry of the complex plane. So now, from now on, if I give you a point in the complex plane, at least geometrically you can locate 1 over z. How? You find minus theta and you measure this distance, find its reciprocal, and separate that point on that line so that its distance to the origin becomes the reciprocal of that line. Yeah, is that clear? Okay, so let us not deviate that much. So now we come back. So we learned that if I give you a complex number, you can immediately write in the polar form, you can immediately write its reciprocal again in the polar form. What you are supposed to do, you take that r, which is the absolute value, and actually do and find the reciprocal of that, and put it here, and whatever you have for the argument, you just multiply it by negatives. Yes? Okay, now let us go back to the question that I wanted to answer. So if I give you these two complex numbers and I ask you to divide them, what is the formula that we will get? Okay, let us see. Okay, so now I am going back here. So Z1 is this and Z2 is this. So I want to calculate Z1 over Z2. But Z1 over Z2, as you know, can be written as Z1 times 1 over Z2. But we just learned what is Z1? Z1 is R1 cosine theta 1 plus I sine theta 1. This is Z1 multiplied by 1 over Z2. Well, we just learned what to do for 1 over Z2. I find the reciprocal of R2, which becomes 1 over R2. And then what I need to do is to multiply the argument by a negative sign. Understandable? And now, instead of dividing, I am again multiplying. But we learned the rule of multiplication, yes? We learned that if I have two complex numbers in the polar form, if I want to multiply them, just multiply these numbers and then add the angles. Yes, I will do the same. So I will multiply these numbers, which becomes R1 times 1 over R2. And then I add this angle to that angle. So this becomes cosine theta 1. I have to add it to minus theta 2, but it becomes just minus theta 2. And then plus I sine theta 1 minus theta 2. Yes? So again, I get a nice relation. You see, if I want to multiply r's, add the angles. If I want to divide r's, but subtract the angles. Yes? And which one should come first? Of course, for cosine, it doesn't matter if theta 1 comes first or theta 2. But for sine, it matters. So first of all, if I am dividing Z1 by Z2, I have to divide R1 by R2, and I have to write theta 1 first and minus theta 2. For cosine, it doesn't matter, but for sine, it matters. So be careful about that. So is that clear? So that is the topic of multiplication and division in polar form. For multiplying, multiply r's, add the angles. For dividing, divide r's, subtract the angles. Okay. But there is one more part that I want to teach, and actually that is the main reason why we are interested in writing a complex number in its polar form. Because usually working with polar form means that you have to work with trigonometry, and that's probably harder than usual working with numbers, yes? Why we are interested in? Because that's a very nice formula, and that is, the topic is this now. Demoir formula. I don't know if I can write it. I think it's a French name, so is there anyone who knows French? Is it Demoir or something? Yeah, let me check. Moivres. Yeah, that's correct. Okay, so this is Demoir formula, and that is extremely useful and probably one of the astonishing formulas in a complex number. It's very important, yes? If I ask you, for example, to motivate you why this is important, is that if I give you a binomial, for example, a plus b, and I ask to square it, of course you have the formula in your head, and you can square it easily, yes? But you know that if I increase this power, this becomes harder and harder, even if you use the binomial theorem in Math 5, we learned in Math 5, yes? But calculating this expansion is actually very tedious if I increase the powers, yes? And this is why raising complex numbers to high powers is hard, because complex numbers are always, more or less always written in form of binomial, Of course, we can have a complex number like 2i as well, but most of the time we have a real part, we have an imaginary part. So if you want, you can understand that there are two terms involved. So if I ask you, for example, 3 plus 2i to the power of 15, in principle, that's a hard thing to do. You have to multiply this 15 times. Principally, it is not a hard problem. It's easy to understand, but it is tedious. But now there is some miracle that happens. There is one exception that this calculation is extremely simple, and that is this expression. If you have this very particular complex number, that the real part is cosine of an angle, and its imaginary part is the sine of that angle. Yes? This is a complex number, but a very specific form of a complex number. The real part turns out to be cosine of an angle, and the imaginary part turns out to be the real part of the same angle. If you have this complex number, if you want to raise it to even power 100, it is a matter of seconds. So what you need to do, of course, in principle, you have to multiply it 100 times. And if you do that, at the end, it turns out that what you need to do is just multiply the angle by 100. Yes? So this means that the answer becomes cosine of 100 theta plus I sine 100 theta. That's it. Yes? So, but this is the discovery of Demoivre. So he realized that if you want to have this particular form of complex number, it is extremely easy if you want to raise it to any power. Of course, if I want to raise it to any power, it means that I multiply 100 times and do a lot of simplifications, but at the end of the day, it turns out to be this. Okay, so this we want to discuss today. Is that clear? That's the idea, yes?
Does it work for negative powers?
Yes, yeah, we will come to that as well. But for here, you only study them for integers, yes? Because fraction powers we haven't talked about yet. Because we haven't talked about what is the meaning of a square root of a complex number. Yes. Did you have any questions? Okay. So that is the idea. So if I have a positive integer or a negative integer, this will work. Yes? And of course for 0, that is also clear, because any number to power 0 is 1. And if I multiply the angle by 0, cosine of 0 is 1, sine of 0 is 0, so it becomes 1. So for 0 also works. Okay, but this is the idea. We want to talk about this. So if I want to write the Demoivre's formula for you here, so let me change the color. So you will see that if n is an integer, yes, then cosine theta plus I sine theta raised to that power, no matter how big power is, this becomes just simply cosine n times that angle plus I sine n times that angle. So that is called the Demoivre's formula. Okay, before going to show why this is true, let us use it to see how it works in action, okay? For example, let us ask you to calculate this. Square root of 3 minus 3i okay, so let me make it positive so don't make trouble for you. So if I want to calculate this to the power of 600, for example, I want to raise this number to power 600. Of course, this is extremely hard if I want to do it the usual way, multiplying 600 times. But if I can write this number in that form, might be I will be able to use the Demoivre's formula. And that is the reason we were interested to change the form of this number from a Cartesian form to a polar form. Because you see, in the polar form, you have the right combination, you know. In the polar form, at least this part is exactly what appears in the De Moivre's formula. And if I ask you to raise this to power 1000, this number will be raised to power 1000, which is not hard. Of course, calculating a number to power 1000 is hard, but that is not we are interested in. But this one to power 1000 makes one problem for me. But that one is solved by De Moivre's formula. Yes, so let us just simplify this. So when, by the way, where if I want to give you a rule in the exam, when do you should think about the De Moivre's formula? You see, they can ask you to calculate this without even mentioning that you use De Moivre's formula. But because you see that this is fairly high power of a complex number, you need to understand that probably the rule is to use the De Moivre's formula. So it means that automatically you need to realize you have to switch to the polar form. Yes, so that is the idea why we learned to switch to polar form in the first place. Okay, so let us calculate this together. So that's the question. We want to simplify this expression as much as possible. So the first thing I do, I will introduce this complex number z, which is square root of 3 plus 3i. And the question mark is, what is z to power 600? Okay, I switch this to polar form. For switching a number to polar form, I need two things, yes? One of them is the absolute value, which is the square root of the real part squared plus the imaginary part squared. So this becomes square root of 3 plus 9 square root of 12, but it can be 4 times 3, square root of 4 is 2, so r becomes 2 square root of 3, yes? And now I have to go and find the argument, yes? So more or less I have to sketch something here for myself. So assume that this is, I don't know, square root of 3 somewhere, and 3 is a little bit more here, so that is 3. And then I have this one to be my z. But then I will actually draw the vector. And then here, the argument is exactly this angle. Yes? And I have to find it. And I told you that always use tangent. So tangent theta becomes the opposite side, which is the length of the opposite side, which is 3 units, divided by the length of the adjacent side, which is the square root of 3. But then 3 can be written as square root of 3 times square root of 3, divided by square root of 3. This one and that one are cancelled. So this becomes square root of 3. If you have it in your memory, that's better. Of course, this you have to somehow use the calculator or use your memory. So in this case, I have it in my memory. At least you know that this is one of the famous angles. Then you have the formula sheet, you can refer to the table. So then if you do this, it becomes pi over 3, 60 degrees. So what I do, now I switch to polar form. So the complex number that you gave me, I can write it in the polar form using r that I calculated and theta that I calculated. So it becomes 2 square root of 3 times cosine pi over 3 plus I sine pi over 3. Yes? And now I am interested in the question mark here. So the question mark, which is z to power 600, means 2 square root of 3 to power 600, and this combination to power 600. Yes? But this one, we have to live with it. So what can I do? I cannot do that much. 2 to the power 600 and then 3 to the power 300. Yes, that's nothing I can do something about it. So I have to write it. Yes, because the square root of 3 means 3 to the power 1/2. So 1/2 multiplied here it becomes. But this one, I have to use the De Moivre formula. So what I have to do, I have to multiply this number by the angle instead of multiplying it by itself 600 times. So what I have to do, it becomes cosine. Let me just be careful here. So I multiply the angle by 600. But mainly you can do a lot of simplifications here. So what is that? Because everyone knows that this one and that one are simplified, so that becomes 200 pi. And that's also 200 pi, by the way. They are the same angles, yes? But where is 200 pi located in the unit circle, on the unit circle? 200 pi is the same point as 2 pi, yes? It's an even multiple of pi. So if you have this, so 200, so if I start here it's 0, when I go back here it's 2 pi, when I go back once more it's 4 pi, so even multiples of pi are here. So 200 pi is easily seen to be here, yes? And then cosine is the x-coordinate, which is 1 in this case, and sine is the y-coordinate, which is 0. So then this one is 1 and that one is 0. But this is vanished, this is 1, so that's the answer. So the answer to the problem is just simply this very big number. Yes? So that is important. Do you remember I told you that if in writing into the polar form, don't continue, because if you continue, you will get the number back. But in contrary, I would say that when the number was not in polar form, I switched to the polar form to be able to use the Demoir formula. There is no reason to remain in the polar form. We switch back again to Cartesian or more standard form. Yes, is that understand? So this picture, this formula tells you that you start with the standard form, you switch to polar form to do your calculation, because Demoir's formula will help us to do that. And then when it is done in polar form, there is no reason to be in polar form, which is more complicated. We switch back to the standard form. So that's the logic that you have to have in mind. Yes, is that clear? Okay. So we have a little bit of time. Let us discuss why the formula is correct. By the way, the formula should be, you should be able to predict that after this lesson. Yes? Because that's more or less the same thing, but if you want to do it properly, you have to do mathematical induction. Because, for example, if I ask you, assume that you didn't know about the name of this guy, I just told you that formula, and then I ask you to raise it to power 3. Could you do it? What is the meaning of this to power 3? It means multiplying this number by itself 3 times. Yes? So if I ask you what is r in this problem, the r is this number, which you don't see is 1. And then what is the angle is theta. Now I am asking you to raise it to power 3, but it means to multiply this by itself 3 times. According to the rule, if I have a complex number in polar form, if I want to multiply 2 complex numbers in polar forms, I have to multiply these numbers, but this number for this is 1, so I have to multiply 1 by 1. And then what happens to the angles? The angles should be added. But if I have the same number, the angles are the same. So if I multiply 3 times, I have to combine them. So if I want to use that formula, this becomes cosine theta plus I sine theta multiplied by another cosine theta plus I sine theta multiplied by another cosine theta plus I sine theta, yes? But according to what we learned, these are the complex numbers in polar form, and I am interested in multiplying them. The rule is to add the angles. So it becomes theta of this angle, but the angles are exactly the same. But no one writes theta plus theta plus theta. People simply write 3 theta. Yes? That's exactly the same thing. But if you want to do it rigorously, you really have to use mathematical induction. Say that, okay, I prove this formula for n equals to 1. That is correct. I assume that this is valid for k. I show that this is also valid for k plus 1. But it is only for positive integers. But I told you that this formula is also valid for negative integers. Let us understand that one. Why do you think that also works for negative powers? So why do you think it will work? Oops, I think it's good to keep this one here. So let me ask you. First of all, cosine theta plus I sine theta to the power of -1. Let me calculate this one. So hopefully you understand that this formula is valid if I have positive integers. But I just told you that this is also valid if you have negative integers. We want to explore that part. So if I ask you, the simplest negative integer is -1. Let us check the formula works here. This formula, if correct, will tell you that this should be equal to what? It should be equal to cosine. -1 should be multiplied by my angle. Is that right? Is this formula correct? Yes, we just calculated here, you see. The only thing is that I started from r, but r in this case is how much? R in this case is 1. So 1 over 1 is still 1, but that is exactly the same formula that I expect. So for 1 over z it works, at least for negative power. But if I tell you raise it to power -2, what do you do? So you would say that raising it to power -2 means 1 over raising it to power 2. Is that right? That's the meaning of negative power. But for positive power, Demoire's formula in the positive case will work. So it becomes 1 over cosine 2 theta plus I sine 2 theta, yes? But I just learned that if I want to find the reciprocal of a complex number in polar form, what I have to do, I have to multiply the angle by a minus sign. Yes, so that what happens, the reciprocal of a complex number in polar form is the same complex number, not the same, is the complex number whose argument is the negative of the argument here. So it becomes -2 theta plus I sine -2 theta. And then if you compare this with the last one, it is as if -2 is being multiplied in again. And then if you want to prove this, you have to prove this again by mathematical induction that this process will continue. But this is extremely simple. So hopefully you see that this formula is correct when I choose in an integer, no matter if it is positive or negative. Is that clear? So now hopefully in a package you understand if someone asks you why we make trouble for ourselves to go to the polar form, you have the answer. Because if I am interested in calculating high powers of complex numbers, if I want to do it in Cartesian form, the only thing that I can do is using the binomial theorem, Newton's binomial theorem, which is also hard. If you want to use binomial theorem here, there are 601 terms. So don't think that this is easy, yes? Even if you want to use that formula. If you want to multiply them, that would be 2 to the power of 600 terms. Okay? If we want to do naively, and by the way, 2 to the power of 600 is a very, very big number. Do you remember at some point I calculated for you, by the way, let me just repeat it. If you have, I will take A4 papers, I want to put them, so you know that if I put 500 of these papers on top of them, it becomes the same thickness of a package of A4 paper. I think you can estimate it 10 centimeters. Now instead of putting 500, let me put 2 to the power of 64 of these pages. And then it will make you a tower, yes, of papers. And then I think one of your lessons, if I remember, we calculate the height of this tower. So, and then it turns out, roughly speaking, it's 6,000 times more than the distance from the Earth to the sun. Yes? And the distance from the Earth to the sun is 150 million kilometers. So 2 to the power of 64 is such an extremely big number, so let alone 2 to the power 600. Yes? So I mean that Even for supercomputers, probably that is not easy if they want to do it in this very standard way, just multiply it 600 times, yes. But even if you use the binomial theorem, you still have to work with 601 terms. But you see that it was manageable without any calculator in a limited amount of time using the Demoir formula. So that is the reason why we make the complex number a little bit more complicated. We pay the price there, but the point is that we can calculate high powers of complex numbers fairly easily. Yes? Okay, so, and let me just remind you again, there is a big list of problems that I uploaded on a school on Google Classroom, because the order in the book was a little bit different from what I saw. When I started teaching, I told you how to multiply, how to add, how to divide, but in the middle of the lesson they are talking about this. So I have already covered that, so don't think that I am jumping. So everything is completely covered until the end of the Demoir's formula. And I will update the Google Classroom. So this formula is extremely important. I really want you to solve the problems in the book. They are very good problems. Any questions? Thank you.